Hey everyone, welcome back to another video. Today we're going to be talking about arithmetic sequences. Last week we did geometric series sequences and sums, and we were looking at sequences where we had a first term that we called a sub 1, and we got each preceding term, each next term, by multiplying it by a common ratio, r. So we got a sequence such as this. An arithmetic sequence is where instead of multiplying by a common term, we're going to add. So, for instance, if our first term we can call a, we then write our second term as a plus d, where d is that common number that we add each time to get our next term. It's called the common difference, which is why we use the letter d. So then you can guess the next term is a plus d, or in other words, a plus 2d, and so on. Until if you have n terms, it's going to be a plus n minus 1 times d. So here you have 0 d's, here you have 1d, 2d's, until you get to n minus 1, so that would be n terms. So today we're going to be looking at how to find the total sum of one of these sequences, so the series of an arithmetic sequence. However, you'll see that for arithmetic series, unlike geometric, we're not going to be able to find what we called last time the infinite sum, where we had an infinite number of terms in our geometric series, and we were able to find that sum. And it's pretty self-explanatory, and I think we went over it in the last video. But if you have, for instance, your first term is 1, and you have an arithmetic series, and let's say that the common difference is 2, so our next term is 1 plus 2, which is 3 obviously, and so on. So you get 5 for the next one, and so on, and you see it's odd numbers. If we add these numbers up, and we have an infinite amount of them, it just keeps going up and up and up and up towards infinity. So that sum is never going to converge, we say. It's never going to stop getting bigger and eventually let us calculate it. Because here, it's just going up. These odd numbers, we know there's an infinite number of odd numbers. So our sum for an infinite arithmetic series is, in this case, infinity, which is why we can't calculate it. However, we can calculate the sum of an arithmetic series when it's finite. Finite means we have an n number of terms, where n is an integer, not infinity. So, firstly, let's take a look at a general example. So, let's say that we have our first term is 2. And let's say that our common difference, so d equals 3 and a equals 2. So by our formula over here, that second term is 5. And we can write in our next few terms as 11 and 14. So I'm going to tell you now that the formula for the sum of a finite sequence or series is S sub n equals n times a sub 1 plus a sub n divided by 2. So if you check on your own and you add up 2 plus 5 plus 8 plus 11 plus 14, you'll see that it equals 40. So now let's just make sure that our formula is correct. So if we plug in for n 5, because n is the number of terms we have 5 terms. A sub 1 is the first term in our sequence, so 2, plus our last term, a sub n, which is 14, divided by 2. So 5 times 16 divided by 2. 16 divided by 2 is 8, so really it just equals 5 times 8, which equals 40. So it does work. But now let's derive why this formula is true. So, like we mentioned earlier, we can write out that sum all in terms of a sub 1. So S sub n, we can write out as a sub 1 plus a sub 1 plus d, because remember we just add a d every time to get the next term, plus dot 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 dot. Let's add our second to last, so a sub 1 plus n minus 2 times d, plus a sub 1 plus n minus 1 times d. So that's our sequence if we have n terms. So that's our s sub n. But now we're going to try and rewrite that. But instead of using a sub 1 to represent every term, as you see here, we have like a sub 1 plus d is our second term. Our second to last term is a sub 1 plus n minus 2 times d. And you see, a sub 1 is in every term. Well, let's try and rewrite that, but using a sub n. So what is a sub 1 in terms of a sub n? Well, remember, this equals a sub n. So a sub n then must equal a sub 1 plus n minus 1 times d, and a sub 1 equals a sub n minus n minus 1 times d. So let's plug in, instead of writing a sub 1 right here as we did, let's write a sub n minus n minus 1 times d. And let's also write in a sub 2 in terms of a sub n. Well, remember that a sub 2 is really just a sub 1 plus d, as you can see here in this second term. So that basically means if we have a sub 1, we just have to add d to that to get a sub 2. Well, it's a little confusing because we're subtracting d's here. So how do we add a d when we're subtracting d's? Well, we can think of it as if we're subtracting n minus 1 d's, in order to make that 1d bigger, we're just going to subtract 1 less d. So essentially what it's going to be is a sub n minus n minus 2 times d. And we can rewrite all of our terms like such, and we get to our last term. Well, let's write in our second to last term. It's going to be a sub n minus d, and our last term is, just a sub n. So now we have two equations. Both are equal to s sub n, but one is in terms of a sub 1, and the other is in terms of a sub n. So what we're going to go ahead and do is add the two equations. So on the left, you get 2 times s sub n equals. Okay, here is where we have to pay close attention to what's going to happen when we add. Some of you may have already noticed that we have plus d's in the top and those minus d terms in the bottom. So when we add, they're going to cancel. So for instance, this plus d right here is going to cancel with this minus d when we add. This plus n minus 1 times d is going to cancel with this minus n minus 1 times d, and everything in between. And we're just going to be left with, well, in the top, a bunch of a sub 1s, and in the bottom, a bunch of a sub n's. But how many a sub 1s and how many a sub n's? Well, there's an a sub 1 in each term in the top, right? How many terms are there? There's n terms. So we have n a sub 1s. And the same applies In the second equation, we have n a sub n's. And we can factor out that n, and we can divide by 2, and we see that s sub n equals n times a sub 1 plus a sub n over 2, just as we said it does. So that's the derivation for a finite arithmetic series, the sum of that sequence. And it's a pretty cool formula, and it's super helpful. And let's take a look at why. Okay, so we have our formula. Now we're going to take a look at an example of a super common arithmetic series that you'll see everywhere in math. Everywhere. So it's simple. It's 1 plus 2 plus 3 plus dot 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 dot. And you could obviously choose how many terms you want. Let's just choose 10. So we have the sum of the numbers 1 through 10. So obviously you could calculate that yourself, but we're going to use our formula. So we have s sub n equals, how many terms do we have? 10 in our case. That's what n equals. A sub 1 is 1. It's the first term. A sub n, or in our case, a sub 10 equals 10 divided by 2. So it's 10 times 11 divided by 2, which equals 55. And if you added them all up yourself without the formula, you would see that that is indeed true. It equals 55. But let's take a look at the general case. So essentially when we have n terms, not 10 as we chose. So a sub 1 still equals 1 because our first term is still going to be 1. And d, our common difference, still equals 1. It's just that our series or our sequence goes to n, and we don't know what n is. But what is our sum? What is s sub n in terms of n? Well, let's see. If we have s sub n equals n, well, n is n. It's the number of terms we have, so we can leave that as is. A sub 1 is 1. A sub n is n. Because remember here, a sub 10 equaled a sub 10 equaled 10. So n equals a sub n divided by 2. And that's it. Our sum for this sequence 1, 2, 3, dot, n is just n times n plus 1 divided by 2. So that means if you have the series 1 plus 2 plus 3 plus dot, 9,456. You're going to have to add up 9,456 terms. Oh, you can just use our formula. S sub n equals n. Well, that's the last number in the sequence always, so 9,456 times. One more than that, 9,457 divided by 2. So your calculator can do that in like 1 second instead of having to manually add 1 plus 2 plus 3 plus dot, 9,456. So it's a super, super helpful formula, as you can see. And this sort of special case for when we have that arithmetic sequence 1, 2, 3, n is also super helpful. So you should try and remember both of these. And now let's take a look at why we can use arithmetic sequences, or I should say how, in competitive math problems. So problems that, we've been doing in those problem sets that are a little bit tricky sometimes. Let's take a look at an example of one of those. So the problem we're about to do is taken from AMC 12. So AMC 12 is one of those competitive math contests. It's called the American Mathematical Contest. And the 12 represents that it's for 11th and 12th graders. That means it's super hard, this test. Because most of you are in middle school or elementary school, you would be taking the AMC 8, which is for 8th graders or younger. This isn't even from the AMC 10, which is for 9th and 10th graders mostly. This is AMC 12, 11th and 12th graders. So it's super hard, this test. But we're going to see how powerful arithmetic series can be. Because we're going to solve this problem super fast, and it's from a super hard test. So let's see what that problem is. It says, a grocer makes a display of cans in which the top row has 1 can and each lower row has 2 more cans than the row above it. So I'm going to do my best to draw some cans. The top row, he said, or the problem said, has 1 can. Each row below it has 2 more. So if we have 1 in the first, we have 3 in the second. And if we have 3 in the second row, we have 2 more in the third row, that would be 5. And it says, if the display contains 100 cans total, how many rows does it contain? Well, if we know that this is the first row, this is the second row, and this is the third row, it's basically saying, well, what's n? How many rows do you have total? But it also tells us that we have 100 cans total. So here we have 1 can, here we have 3, here we have 5. It's not saying that the last row has 100. No, it's saying if we add up all of these rows, we have 100 total. So if we relate this back to arithmetic series, S sub n, this quantity right here, equals 100. So 100 equals n, because n is our number of rows, and we don't know that. They're asking us for that. So we can just leave it as n, times open parentheses, a sub 1, which is just how many do we have in our first row? Because if we think of each term in our sequence being 1, 3, 5, dot, 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 well, a sub 1 equals 1 then, because we have 1 in our first row. How many do we have in our last row? Well, we don't know exactly, but what we do know is that, we can write a sub n as a sub 1 plus n minus 1 times d. Well, we know a sub 1, we just wrote it. It's 1 plus n minus 1. Remember, we don't know n, but we want to solve for n, so we're going to leave that in there, times d. What is d? Well, it's the common difference between each row or each term, so 2, because they told us in the problem that each row below the one above it had 2 more. So d equals 2. So, well, what can we write? And remember, we have to divide by 2. Well, what can we write now in our formula? How can we simplify this so that we can solve for n? Because right now, it kind of looks like a mess. But we do know that we have one variable, n, and one equation, so we must be able to solve it. So first, let's simplify the most inside parentheses, the one that's most inside. So that would be 1 plus open parentheses 1 plus 2n minus 1 divided by 2. So we simplified that most inside parentheses, this one right here, and we multiplied out. Oh, sorry, this should be a 2, not a 1, because we have 2 times n minus 1, so it should be 2n minus 2. So now we just have to simplify even more, and we should be able to solve for n, which is what they asked us for. So how can we simplify this further? Well, we can rewrite the 100. We have n times 1 plus 1 plus 2n minus 2 over 2. Well, those 1's and that 2 cancel. So we're just left with 100 equals 2n times n over 2, Well, those 2's cancel. So we're just left with 100 equals n squared. So n equals the square root of 100, which is 10. So we have 10 rows. And we solved the problem. And all that super messy math and algebra just sort of canceled out and became super nice. And we solved this problem pretty easily just using arithmetic series. So another thing to note though would be that we got n squared as the sum of the sequence. So some of you may have recognized, well, what is that sequence? It's odd numbers. It's 1, 3, 5, 7, and so on. So if we got n squared as the sum, does that mean that the sum of n odd numbers is always n squared? Yeah, it does. Because let's take a look at it. Let's add 1. Well, we get 1. Is that 1 squared? Yep. What's 1 plus 3? 4. Is that 2 squared because we have 2 terms? Yep. What's 1 plus 3 plus 5? 9. Is that 3 squared? Yup. What's 1 plus 3 plus 5 plus 7? 16. Well, that's 4 squared. So not only did we solve this problem, but we learned that the sum of n odd numbers equals n squared. So that's pretty helpful and kind of amazing that those odd numbers just add up to such a nice quantity, n squared. So that's going to be all for today's video. I hope that you enjoyed it and learned something, because arithmetic sequences are pretty common, but they're super useful. They can really simplify some sort of mind-numbingly hard series and sequences that would be really annoying to either have to do by hand or just sort of impossible. And we learned a few special cases where we had that first sequence that was 1, 2, 3, 4, ... n, that equaled the sum n times n plus 1 over 2. And we just learned about odd numbers. The sum of n odd numbers is n squared. So hopefully you enjoyed, like I said, and we're going to be sending out a problem set that does have some problems involving arithmetic sequences and maybe a little bit of geometric from last week. And as always, if you have any questions, don't hesitate to email us, no matter what they're about. If it's about math, scheduling, anything, just email us and we'll get right back to you. So thank you for watching and good luck in your problem set. Wrote it.